Thanks for dropping by during my office hours. As promised, today's video will delve into a detailed discussion on estimating the required fire flow. Impact on distribution system design. The choice to supply water for fire protection necessitates a utility to thoroughly factor in fire flow requirements when sizing pipes, pumps, and storage tanks. While in larger systems, fire protection has a marginal impact on sizing decisions. In smaller systems, these requirements can result in a notable increase in the size of various components. Overall, the influence of providing water for fire protection varies, with minimal impact on the substantial components of major urban systems and a significant impact on smaller distribution systems. The most notable impacts include the installation and upkeep of fire hydrants, ensuring sufficient storage capacity, and adhering to minimum pipe size requirements in neighborhood distribution mains when smaller pipes would suffice for delivering potable water only. While these requirements streamline the design of distribution systems for engineers, they also incur higher costs for the water utility. Additional impacts encompass the need for extra treatment capacity at plants and increased pumping capacity at pump stations. Fire flow requirements. When formulating a fire protection plan, the governing body must initially adopt a well-documented procedure for determining the fire flow requirement. Essential to ensuring an adequate water supply is defining how much water should be made available for various scenarios. The needed fire flow is defined as the rate of water flow at a residual pressure of 20 psi or 138 kilopascals and for a specified duration, necessary to control a major fire in a specific structure. A comprehensive definition of needed fire flow entails determining both the required flow rate and the total amount of water needed to control the fire. The rate of flow and the duration of flow required can be specified by the simple equation here. Quantity equals to rate multiplied by the duration of flow. Recognizing the significance of both flow rate and total quantity is essential in comprehending how water is employed to extinguish fires. The application of water in firefighting serves two primary purposes. Firstly, it dissipates the heat generated by the fire, preventing this heat from elevating the temperature of unignited material to its ignition point. As water transforms from a liquid to a gaseous state, it absorbs the fire's heat, releasing it as steam. Secondly, the portion of water not converted to steam by the fire's heat remains available to cool materials that have not yet ignited. Additionally, water acts as a blanket over unignited material, restricting the oxygen necessary for combustion initiation and sustenance. Calculating needed fire flow. Every fire is inherently unique due to unpredictable variations in the structure and contents of the burning building. Exposures, defined as the configuration of adjacent structures not involved in a fire but that are to be protected to prevent the fire from spreading. Weather conditions, temperature, and the duration of the fire. Consequently, various methods have been suggested to ascertain the adequate amount of water needed to extinguish a fire. In this video, the method developed by the Insurance Services Office Incorporation, or often known as the ISO method, will be discussed here. Insurance Services Office Method. The Insurance Services Office Method, or ISO method, is documented in its publication, Fire Suppression Rating Schedule. The term used in that document to describe the fire flow requirement is needed fire flow, or NFF. The NFF represents the required flow rate to control a major fire in a specific building for a defined duration. Its purpose is to evaluate the adequacy of a water system, forming a component of an insurance rating schedule. While not intended as a design criterion, it has been demonstrated that the NFF reasonably aligns with the actual flow required to suppress a fire in real-life situations. A water supply should have the capacity to deliver the maximum NFF within its distribution system area. When designing a new water distribution system or implementing improvements in an existing one, it is common practice to accommodate the NFF within the design area. However, it is uncommon for an existing water distribution system to be capable of meeting every NFF within its service area. The ISO classification of a community's water system hinges on the available flow rates at representative locations, with an NFF of 3,500 GPM or less, as determined by its fire suppression rating schedule. Private and public protection at properties with larger NFFs undergoes individual evaluation and may deviate from the community's classification. The computation of a NFF in gallons per minute for a subject building takes into account its construction factor C, occupancy factor O, exposure factor X, and communication factor P, as delineated below. Construction factor, C, the segment of the NFF assigned to the type of construction in the area in square feet of the subject building is calculated using the following formula. The construction class coefficient F is related to the class of construction as listed in the table here. The effective area A is the total area in square feet of the largest floor in the building, augmented by a specified percentage of the other floors. For buildings of construction class 1 through 4, it includes 50% of all other floors. For buildings of construction classes 5 or 6, provided that all vertical openings in the building have 1 hour or more protection, it consists of 25% of the area, not exceeding the 2 largest floors. The doors must be automatic or self-closing, labeled as Class B fire doors that provide 1 hour or more protection. In other buildings, it involves 50% of the area, not exceeding 8 floors. The upper limit for C is constrained by the following: 8,000 GPM for construction classes 1 and 2, 6,000 GPM for construction classes 3, 4, 5, and 6, and 6,000 GPM for a single-story building of any construction class. The lower limit for C is set at 500 GPM. The computed value of C should be rounded to the nearest 250 GPM. Occupancy factor, O. The occupancy factors, given in the table here, reflect the influence of the occupancy in the subject building on the NFF. The figures here have provided representative lists of occupancies by combustibility class. Exposure factor X, and communication factor P. The exposures and communication factors reflect the influence of exposed and communicating buildings on the NFF. A value for X plus P shall be developed for each side of the subject building as shown in the equation here. The exposure factor X depends on the construction and length height value of the exposed building and the distance between facing walls of the subject building and the exposed building. The length height value is calculated using the length of the wall in feet times height in stories. This factor should be selected from the table listed here. When more than one exposure side exists for the subject building, apply only the largest factor X for that side. When there is no exposure on a side, X equals to 0. The communication factor P is contingent on the safeguarding of communicating party wall openings and the length and construction of communications between fire divisions. This factor should be chosen from the table here. In cases where more than one communication type is present in any one side wall, only the most substantial P factor for that side should be applied. If there is no communication on a side, P is equal to 0. Needed fire flow. The calculation for NFF follows the equation listed here. In cases where a wood shingle roof covering on a building or exposed buildings could potentially contribute to the spread of fires, an additional 500 GPM is to be added to the NFF. The NFF is subject to a maximum limit of 12,000 GPM and a minimum limit of 500 GPM. If the NFF is less than 2,500 GPM, it should be rounded to the nearest 250 GPM, and if greater than 2,500 GPM, rounding should be done to the nearest 500 GPM. For 1 and 2 family dwellings not exceeding 2 stories in height, refer to the NFF values listed in the table here. In the case of habitable buildings not covered by this table, the NFF is capped at 3,500 GPM at maximum. For a building equipped with automatic sprinklers, the NFF should account for the sprinkler system's requirements plus hose streams converted to 20 psi or 138 kilopascals residual pressure, with a minimum of 500 GPM. Detailed specifications for sprinkler water requirements at the base of risers can be found in the National Fire Protection Association Standard Number 13. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.